Dear students, we talked about some of the classical experimental observations which could not be explained in classical mechanics in the previous classes. We talked about blackbody radiation. We talked about variations of the specific heat of monoatomic solids. Then we talked about the photoelectric effect in the previous classes. Now I am going to talk about the Compton shift. Compton shift is the difference in the wavelength of incident and scattered radiation when the photons strikes an electron. The incident radiation and the scattered radiation has a difference in the wavelength, and this observation was known. Okay, according to classical theory, what it should be that on the collision after the scattering there should not be any change in the wavelength. Okay, and what classical theory tells you that the incident radiation and the frequency of the scattered radiation should not depend upon the direction. So it should not depend upon the theta value also. Okay, but what happens that Compton observed that the radiations which is incident, which is striking the electron, and the radiation which is scattered has different wavelengths, and this difference in the wavelength is dependent on the theta function. So if you look at this picture, then here we have an incident electromagnetic radiation. This is electromagnetic radiation. Electromagnetic radiation which strikes the electron at rest, and if the electron is at rest, it will not have any mass, m is equal to 0, and as per Einstein's equation, the energy should be equal to m naught c square. So initial electron is at rest. When the photon collides with this one, it transfers some momentum to the electron also, and this is your scattered photons. A scattered electromagnetic radiation goes into this direction, and electron goes into this direction. Okay, so what happens that if you look at the energy and the momentum before the collision and after the collision, then this picture, this is the before the collision, this is also before the collision. Okay, so this is for the electron, this is for the electron, and this is for the electromagnetic radiation. So before the collision, you have E1 is equal to m naught c square, and m1 is the momentum. M1 is actually momentum, not mass. So this is 0 because the velocity is 0. Now for electromagnetic radiation, we have E is equal to h nu, and for nu we can write c divided by lambda, so hc divided by lambda, and then momentum m is given as mass into velocity. So this is mass into velocity, and this comes out to be h divided by lambda. For an explanation of this, since E is equal to mc square, so m is equal to E divided by c square, and you know energy is h nu, so h nu divided by c square, and again we can write nu, instead of nu we can write c divided by lambda, so it is hc divided by lambda c square, and then c and c will go, and you have h divided by lambda c. H divided by lambda c, and then if you use this one h divided by lambda c here, then you get h divided by lambda. So this is before the collision. After the collision, what happens? The electron gains energy. I have shown it by a prime. Prime tells you that after the collision. The electromagnetic radiation, the same formula we can use. So hc divided by lambda prime is the wavelength after the. So lambda prime is wavelength of a scattered radiation. Okay, and then momentum becomes h divided by lambda prime. Okay, so same relationship, hc divided by lambda, h divided by lambda, but with a different wavelength, lambda prime wavelength. Okay. And now if you look at the electron after the collision, then electron also gains momentum, some momentum from the striking photons, and now we have m1 prime again after the collision, electron after the collision. So energy again mca square, you know, this was the electron at rest. So energy is m naught ca square, m naught is the rest mass, and m is the moving electron mass. Theory of relativity tells you that these two will be different. So even prime will be mca square and then mv. So this is after the collision on the right hand side and before the collision on the left hand side of the graph. Okay. Now if you look at this, this is what happens when a photon collides with an electron. And if you look at the values of energy and values of momentum, and you apply the law of conservation of energy and law of conservation of momentum, see what happens, what kind of equation you get. See, applying the law of conservation of energy, energy before the collision becomes equal to energy after the collision. So hc divided by lambda m naught ca square. You see, m naught ca square is the energy of electron at rest, and hc divided by lambda is the energy of photons before the collision. After the collision, the energy of becomes equal to hc divided by lambda prime, and you have mca square electron energy. Look at this, the previous diagram. You see, m naught ca square is the energy before the collision, and hc divided by lambda is before the collision. After the collision, you have hc divided by lambda prime and mca square. You rearrange this one, and you get hc divided by lambda minus hc divided by lambda prime is equal to mca square minus m naught ca square. We have given a equation number 1. Okay. So what happens with the momentum? A momentum is a vector quantity, and you see, since it's a vector quantity, so what you can talk about is the x component and y component of the momentum. So x component is the component along this direction, y component is the component along this direction, and if you look at this one, the x component of the momentum we can write as before the collision you do not have a momentum here for the electron, but for the radiation you have a momentum value of h divided by lambda, this one, h divided by lambda. So you have momentum h divided by lambda, and h divided by lambda is the momentum along the x direction. Okay. But after the collision, if you look at the momentum, after the collision, the electromagnetic radiation is moving along this direction with an angle theta, and electron is moving in this direction with an angle phi. So the x component of mv and x component of this h divided by lambda prime you will have to take, and so that component is this one, h lambda divided by h lambda prime cos theta and mv cos phi. Okay. So x component becomes like this one, that this is before the collision. Before the collision, electron is at rest, so the zero momentum is there. Electromagnetic radiation is along the x-axis, so that doesn't change it is divided by lambda. But after the collision, the direction changes for the photon also and for the electron also. And when the photon is moves, it moves from the x direction with a theta angle, and when the electron moves, it moves from the x direction with a phi angle. It changes the direction. So both electron momentum and photon momentum x component we have to take. As far as y component is concerned, before the collision there is no momentum, because along the y axis you do not have any momentum. So before the collision it becomes 0. But after the collision we can talk about the momentum, h lambda prime sin theta and mv sin phi. Okay. So these two should be equal. So law of conservation of energy tells you that the energy should be conserved before the collision, means energy before the collision, energy after the collision should be same. Same way, law of conservation of momentum tells you that the energy before momentum before the collision and momentum after the collision remains same. Okay, so the only thing is that for energy there is nothing like components, but for momentum we have component. Since momentum is a vector quantity, so you need to take x component and y component. So we got these three equations. One is x component of the momentum, another is y component of the momentum, and the energy equations. Using these equations, what we can do, we can rearrange the equation 2 as mv cos phi is equal to h lambda prime cos theta. Okay, up to this I hope it's fine. Now, if we use this equation mv cos phi s lambda divided by h lambda prime cos theta, and we square both sides, then what do you get? You get m square v square cos square phi is equal to h. Now it's a minus b whole square. So what you write? H square divided by lambda square, h square by lambda prime square cos square theta, and minus 2 h square lambda prime cos theta. Okay. So from equation 3 we have mv sin phi. From equation 3 the mv sin phi is equal to h lambda prime sin theta. So let's see. mv sin phi is equal to h lambda prime sin theta. Okay. Now if you square both sides, then again here you get m square v square sin square phi is equal to h square lambda prime square sin square theta. Okay. Now using equation 4 and 5, you see the LHS of both. What we do? Adding these two equations, it's mv square sin square phi and it's mv square cos square phi. So what you can write is mv square cos square phi plus sin square phi becomes equal to this plus this one, h square by lambda square plus h square by lambda prime square cos square theta. Wait. If you rearrange this one, you can get you might get a negative sign also, which you will square, it will omit, so that has been omitted, no issue. So this becomes equal to this the whole equation, 1 2 3 terms here, 1 2 3 terms here, 4th term here. So you have 1 2 3 and 4th term here. Okay, so all we have copied it. Now you see, if you rearrange this one, cos square phi plus sin square phi is equal to 1. So this will be m square v square on the LHS, and on the right hand side you have h square by lambda square 2h square by lambda prime cos theta plus h square by lambda prime square, and again cos square theta sin square theta, this will also be equal to 1 because cos square theta. So we have cos square theta here and we have sin square theta here, and on both sides you have h square by lambda prime square. Here also you have h square by lambda prime square. So you can take it common and this will be equal to 1. And as a result, what you have? You have m square v square is equal to h square by lambda square minus 2h square lambda prime cos theta plus h square by lambda prime square. Okay. Now you have h square everywhere on the right hand side. So take h square as a common and you have m square v square is equal to h square 1 by lambda square plus 1 by lambda prime square minus 2 divided by lambda prime cos theta. Now we apply the theory of relativity. I said you that electron that must have a mass equal to m naught, and electron with a velocity v has a mass of m. So if you use the theory of relativity, then the mass of a moving electron can be written as m is equal to m naught root under 1 minus v square divided by c square. And if we put v by c is equal to beta, then the equation is m naught divided by root under 1 minus beta square. So this you get from the theory of relativity. If we put this value in the previous equation, equation 6, you see m we have, and here you have m square v square. So instead of m square v square, you can write m naught square divided by 1 minus root beta, 1 minus beta square, sorry, root beta naught. Okay, and then v square remains and RHS remains same, which was in equation 6. Okay. Now we can rearrange this equation, and for your convenience I have done every step. So m naught c square then we can write beta square plus 1 minus 1, that you can do easily, and then 1 minus beta square. And then as a result of this, what you get, m naught c square divided by 1 minus beta square minus m naught c square, okay, is equal to right hand side, there is no change, it remains same. Now m naught c square 1 minus beta square, bring this on right hand side and you get equation number 8, okay. From the law of conservation of energy, we have obtained the equation number 1, and that is hc divided by lambda minus hc divided by lambda prime is equal to mc square minus m naught c square. So if you rearrange this one, means divide it by c, you get h divided by lambda minus h divided by lambda prime is equal to mc minus m naught c, and this on rearrangement gives you an equation equal to h divided by lambda prime h divided by lambda prime m naught c, h divided by lambda prime m naught c becomes equal to h divided by lambda prime m naught c divided by root under 1 minus beta square, okay. Then you rearrange and square this equation. So what happens? H divided by lambda, this part goes to the left hand side, minus h divided by lambda prime plus m naught c, then you have squared this one and you square right hand side also, so it becomes m naught square c square divided by 1 minus beta square. So look at this equation, equation number 9, and the previous equation, equation number 8. In the equation number 8, on the right hand side you have m naught square c square 1 minus beta square, and in the next equation, equation number 9, you get m naught square c square 1 minus beta square on the right hand side. So these two sides, LHS of this equation number 9 and RHS of equation number 8 will be equal. So we equate these two. And if you equate these two, many terms go away. Look at this one. First we expand this one, and then you can easily see that all these terms, this goes with this one. This goes with this one. I have changed the color also so that you do not, this goes with this one, okay. So these terms get omitted. Now what happens? If you, the remaining terms, if you look at it, will 2h m naught c divided by lambda minus 2h m naught c divided by lambda prime is equal to 2h square lambda prime minus 2h square cos theta divided by lambda prime. And then 2h m naught c is a common term, so you can take it outside, and then within the bracket you have 1 by lambda minus 1 by lambda prime, which you can write very easily by delta lambda, difference in the wavelength of incident and scattered radiation. That's lambda prime minus lambda is delta lambda, okay. So this we can write, and what you get is that delta lambda, change in the wavelength of the incident radiation and the scattered radiation, is equal to h divided by m naught c 1 minus cos theta. So this Compton shift is dependent on theta direction also, and there is some value of, there is a change in the value of incident radiation and the scattered radiation. This observation remained unexplained in the quantum mechanics, in the classical mechanics. And what we have used? We have used E is equal to h nu in order to explain this one, and what we have used is theory of relativity. Using these two theory of relativity, Compton gave an explanation for the change in the wavelength of incident radiation and the scattered radiation. So again we see that the hypothesis which was given by Planck again was utilized in order to deal with another experimental observation, that was the shift in the wavelength of a scattered and incident radiation when electromagnetic radiation strikes an electron, okay. So this is how the hypothesis gets established when it starts explaining many other experimental observations, and that's what is my motto, to tell you that how the quantum mechanics came into existence gradually. the one hypothesis was proposed in 1900, and then you see in 1905 Einstein used that hypothesis in order to explain the photoelectric effect. Then again in 1907 he gave the equation for the dealing with the specific heat of monoatomic solids. Then around 1913-14 Niels Bohr gave the atomic model, and that explained the hydrogen spectrum. Okay, and then in 1923 this Compton shift was also explained using E is equal to h nu. That was purely a hypothesis given by Planck for dealing with the black body radiation. Okay, so gradually we see that each of the experimental observations which we have talked about are being explained using the Planck's hypothesis. Okay.